In an NMR spectrum, each chemically unique proton produces its own peak. Looking at methane, we see all 4 protons or hydrogen atoms are identical. Each one is only one away from the carbon. Same thing in ethane, there is only one chemically unique proton here. Here's a carbon with a hydrogen one away. Here's a hydrogen one away, hydrogen one away from the carbon, hydrogen one away from an identical carbon, right? This is a symmetric molecule. Hydrogen one away, hydrogen one away. But now in propane, we see 2 types. Here's a hydrogen that's one away from the carbon on the end. And here's a hydrogen that's one away from the carbon on the end. But here's a hydrogen that's one away from the carbon in the middle. The hydrogens that I'm circling right now are identical to each other. The hydrogens with squares are chemically unique. There are 2 types of protons here. In your prelab, you're asked to identify the 3 types of hydrogens in hexane. The bigger the area, the more protons are being used to produce it. Again, looking at propane, I see there are 6 hydrogens that are attached on the end, but only 2 that are attached to the middle. So I would expect this type of proton would produce the larger peak. Again, you're asked to produce the same analysis for hexane. The number of lines a peak splits into depends on the number of hydrogen neighbors that the peak has. The number of lines follows the n+1 rule. Going back to methane, where there are no neighbors here, right? Each hydrogen is identical. So I see one peak and it's not split into anything. It's just one peak. But when I look at propane, so if I take this hydrogen, for example, okay, this hydrogen is the same, 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 which means it has 2 neighbors. And so this peak should be split into n+1, 3 peaks. This was the bigger peak, right? And it is. When I look at this hydrogen, it has 1, 2, 3, 4, 5, 6 neighbors. Again, this is the same hydrogen. So it should be split into n+1, 7 peaks, and they're small. You can see that there's 7 peaks here. When a proton is located close to an electronegative group, it will shift downfield on the spectrum. Downfield means that the peak is located further to the left. When I compare regular propane, where my peaks are at, let's see, a little under 1 and a little under 1.5, and I replace one of the hydrogens with a more electronegative atom like chlorine, what I see is that the peak where the one where I didn't change anything moves a little bit, but the one where I actually changed it shifts down to what, almost 4. So it shifts downfield.